Hello everybody. Today we'll start with our next lecture of structural analysis 2. We'll start with our first unit, that is unit number 1, slope deflection method. We have seen some basics about slope deflection method in your structural analysis 1. Before starting this, we will see first what is the meaning of structure. In civil engineering point of view, a structure can be said as it is the group of elements or the group of structure elements like beams, columns forming a structure which is called as a structure. That is, if I consider any one 3D diagram of a portal frame of any building, suppose the ends of which are completely fixed, right? What are these elements which are here? Those are the horizontal elements that we can say as beams. These vertical elements that we can say as columns. The combination of these two members forming a frame like a structure that we called as a basic structure. We have to analyze this structure. The meaning of analysis is what? That is, we have to find out some structural behavior of this complete member over there. That is, we have to find out the bending moments occurring in this, the shear forces occurring in this, the axial forces occurring in this, and depending on this type of forces, we can see how this beam will bend or how this beam will behave. Accordingly, we have to design these beams for your structural design purpose further. Now, we'll start with our unit number 1, that is slope deflection method. Already, we have seen some basic study about slope and deflection in your structural analysis 1. Then, we'll start with our first, that is meaning of slope. What is slope? We have seen that slope is what? Suppose if I consider any simply supported beam over here which is loaded with a certain UDL, suppose, and due to this UDL, how this beam will bend, or the elastic curve of this bend beam then will be drawn in this way. Then what our slope definition says? It is the tangential line drawn to these elastic curves making a certain angle theta. That angle we call it as a slope. Suppose this is your point A, this is your point B. So slope at point A, that will say as theta A, and slope at point B, that will say as theta B. This is what? This is the initial line of your curve, and this line you can say as the elastic curve. The tangential line drawn to the elastic curve forming an angle, that is the angle theta, gives the slope over there. So depending on the support conditions also, your slope values will vary, or where it will occur, where it will not occur. That conditions will occur depending on your this support conditions over there. Then secondly, the second part, that is what? It is the deflection. Deflection, we denote it by delta or in this way. In both the ways, you can denote the deflection over there. Deflection is what? It is the vertical displacement of initial point to the final point on the elastic curve, that we call it as a deflection over there. That means at every point in this considered beam, your deflection will be different over there. So if you consider, suppose this point is my C, so deflection under that point C, that will be delta C. We have seen different methods for calculation of our slopes and deflection in your AC1, like methods as Macaulay's method, moment area method, again Cauchy-Linus first theorem, second theorem. In all those methods were determining the slope over there. But whatever those methods were based, those were based for determinate type of structures. In Castellan's second theorem we have seen indeterminate structure, but mostly in essay 1 you have studied the determinate type of structure. Basically what we'll do first, we'll try to revise some basic concepts of your essay 1 over there. Basic concepts means what is meant by a determinate structure, what is meant by indeterminate structure, then what is meant by degree of freedom, in that degree of indeterminacy that we'll see. Okay, so first of all, meaning of determinate structure over there. What is meant by determinate structure? The structure which can be completely analyzed by using three conditions of equilibrium, that is three equilibrium conditions which are sufficient to analyze that structure, will call that structure as your determinate structure. So which are those three equilibrium conditions? These are dependent on your two type of structure. First structure is your plane structure and second structure is your space structure. We'll deal with only plane structures over here. So for plane structure, here how many conditions are there? Those are equal to 3, and for space those are equal to 6 equilibrium conditions. Okay, so in plane we'll deal with only plane structure. So in plane structure, these three equilibrium conditions, which are those? That is your summation of moment, then your summation of horizontal forces, and your summation of vertical forces, that is summation of m, summation of fx, and summation of fy. So if these three conditions are sufficient to analyze the structure completely, that is analysis means what? That is we have to find out bending moment in it, shear forces at every point, bending moment at every point. If these three conditions are sufficient, that structure will call it as determinate structure. If not, that structure will call it as indeterminate structure. So how we can define indeterminate structure over there? That is, if the conditions of equilibrium are not sufficient to analyze the structure, that structure will call it as indeterminate structure. That means what will happen in that, your how much conditions you will need, that those will be more than your equilibrium conditions over there. That means some extra conditions you need for analysis of this structure. Okay, so in indeterminate structure, first we need to find out the indeterminacy. This indeterminacy, these are in two forms over there. Which are those? That is static indeterminacy, and second, that is your kinematic indeterminacy. We denote static indeterminacy by ds, and we denote kinematic indeterminacy by dk. First we'll see about static indeterminacy over there. Static indeterminacy, this is the number of basic unknowns at the support or at the joints over there. That is, this static indeterminacy ds, it is given by r minus equilibrium conditions, those are equal to 3. So ds, that is equal to r minus 3, where r is what? Here r, that is the number of reactions available to you. Number of reactions available to you. That means if I consider any beam which is hinged at one end and which is having roller support at the other over there, so number of reactions at your hinged end will be equal to 2. Suppose this is your point A, this is your point B. So this horizontal reaction, that will be your HA, this vertical reaction, that will be your VA, and at point B there is roller support, so here only one vertical reaction will be having, that is suppose equal to VB. So total number of reactions are 1, this will be your second, this will be your third. So total number of reactions are, that will get equal to 3. So if you find out this ds value, that is 3 minus 3, that will be equal to 0, suppose. Okay, what this 0 indicates? That is, there is no any static indeterminacy in this complete structure over there. If some values come over here, that means what? There is somewhat static indeterminacy in this structure. In SA1, you have seen for this static indeterminacy, these are also of two types. That is DSE, this is the combination of two indeterminacies, that is DS, that is the combination of DSE and DSI, where DS is what? That is the external static indeterminacy, and DSI, that is the internal static indeterminacy. In cases of trusses, we have seen that is static indeterminacy, it is given by m minus 2j minus 3, where m is what? That is the number of members in that truss, j is, those are the number of particular joints in those truss over there. Only thing is what? In normal structure, whatever joints you are considered, those joints will be your rigid joints. That means if I consider this frame over there, what are these joints we see over here, those will be your rigid joints over here. And in case of truss, suppose I consider any simple truss over here, in this way suppose. Okay, so whatever these joints occur in this truss, these will be your pin joints. So depending on this particular joints, we have to formulate your ds values over there. Next is your decay values. Decay is what? It is the kinematic indeterminacy. Basically this is also dependent on your support conditions over there, but at this support, what this is, where your slope values, that is theta values, and where your deflection values, that is delta values, will occur or not. On these considerations, your decay value is dependent, or simply we can say these are nothing but non-zero joint displacements. These are called as non-zero joint displacements. On these values, your decay values will occur. We have seen table in your SA1, that is at every type of support, that is at hinge support or roller support, fixed support, free end, how much decay values will be there. That chart you have to refer for this. Okay, then next concept, that is your fixed end moments over there. We have seen one more table regarding fixed end moments over there. Depending on both the ends of your beams are fixed and what a certain loading will be given in that. So fixed end moment occurring at this end, that will be your MFAB, that is fixed end moment of joint A, B, and second one, that is a fixed end moment for joint BA for, okay. You'll refer again those table, that is if point load is at the center, if point load is at the non-uniform distance, that is at A distance from point A and B distance from point B, if UDL is present over there, if UVL is present, that chart you have to refer again for this. Okay. So now here onwards we'll start with your unit number 1, that is slope deflection method over there. Now in this method, basically what you have to deal with the transverse displacement at the ends and transverse slope at the ends of any member over there, which is related to your this basic unknowns over there. Mostly in your slope deflection method, we'll deal with ds number of unknowns over there, that is degree of static indeterminacy. We will need to calculate in our very first step of every numerical. Okay, now basically in any structural member, how your bending moment occurs? Bending moment occurs due to 3 types of conditions. First, if it is subjected to transverse loads. Okay. Secondly, if it is subjected to transverse displacements. And then thirdly, if there are some external rotations applied at the ends over there. Rotations applied at ends of any structural member. Now if your rotations are occurring or due to your transverse loads and due to your transverse displacement, whatever, if your support is undergoing this type of bending moments over there, then it is subjected to far end moments and the near end moment over there. It is subjected to far end moment and near end moment depending on your slope and deflections. Okay, so for far end, considering the slope over there, that value, the far end moment, that is equal to 2ei theta upon L, where theta is what? Theta, it is the slope occurring at your that particular end over there. Whereas your near end moment, that will be equal to twice of this, that is it will come equal to 4ei theta upon L. Remember these two conditions always, that is far end moment, it is subjected to 2ei theta upon L, while your near end moment, it is subjected to 4ei theta upon L. These are what? These are the moments occurring due to rotation applied at the ends over there. Okay. Second thing, we'll see about the transverse displacements over there. Due to transverse displacement, if your rotation comes clockwise or if your rotations come anti-clockwise, it is subjected to bending moment of, that is transverse bending moment of equal to 6 EI delta upon L square. It is subjected to 6 EI delta upon L square, where delta is what? It is the again vertical displacement occurring at that particular point where you are going to calculate this bending moment over there. Whereas in both these conditions, 2 EI theta upon L, that is far end moment, 4 EI theta upon L, that is near end moment, and due to transverse moment, that is 6 EI delta upon L square, this EI, that we'll call it as flexural rigidity. This may vary according to your member specifications also. Okay, so if you consider for horizontal members or for vertical members also, these values will remain same over there. Only some sign conventions will be there that will see while numericals, but during the sign conventions usage, you have to find out the slope deflection equation over there. So we'll move for our next topic, that is we'll find out the slope deflection equation over there. Okay. Due to the sign convention, what I'll do, I'll consider this as plus or minus over there. Okay. Now moving to slope deflection equation over there. Suppose what I'm doing, I have to formulate the slope deflection equation. Okay. Suppose what I'm considering a member, suppose AB. It is not subject to any type of support. Suppose I am supporting it in this way, that is joint A and joint B. Secondly, what I am assuming that both the joints, that is joint A and joint B, both are maintaining the fixity over there. That is, I am fixing both these joints over there. So what will happen? Due to this fixing both the joints, what will occur here? Here your fixed moment, that is MF AB, and fixed moment at your next joint, that is MF BA, will occur, so considering the certain loading on this. I am not showing the loading over here, but certain loading will be given. Due to that loading, your fixed moment in member AB and fixed moment for member BA, that will occur over, or simply you can say fixed moment at joint A and fixed moment at joint B. Secondly, this is called as your process of relaxation of the supports over there. Secondly, what I am doing, I am maintaining the fixity at my joint B and I am releasing my fixity at joint A. That is, I am maintaining fixity over here and here what I am doing, I am releasing it, releasing fixity. Okay, so due to this what will happen? Now if you see the slope value, that is theta, if your both ends are fixed over there, your slope value comes equal to 0. But here your at joint A there is no fixed support, at joint B you are having fixed support, so slope at point B will be completely fixed while slope at point A will be occurring over there. That means what? If you try to draw the elastic curve of this, it will be somewhat in this way. Okay, which will be seen that this will make a certain angle with your joint A, or we'll call it as slope at point A, theta A over there. Okay, due to this slope at point A, we are considering joint A and joint B. Slope is occurring at your joint A, so this will be considered as your near end and this will be considered as your far end over there. So if you see, the near end moment will occur at this joint. We have seen the near end moment is how much? That is equal to 4 EI theta, and that theta is equal to theta A divided by L. Same way, if this is your near end, this will be your far end over there, and at far end your next moment will occur, that is far end moment 2 EI, again theta, we are considering A point only, so theta A divided by L. Getting this? What we have done, we have just maintained fixity at joint B and we have released the fixity at joint A. Due to releasing this joint, this slope will occur at point A. That slope will possess a moment occurring at point A and B, that is equal to near end moment 4 EI theta A upon L, and this will be equal to 2 EI theta A upon L. Okay, now Next time what I'm doing, I'm interchanging these two conditions over there. That is, I'm maintaining the fixity at joint A and I'm releasing the fixity of joint D. Here what I'm doing, here I'm releasing and here I'm maintaining. Okay, so what will happen now? Now slope at your point A will be completely 0 and slope at point B will be having some value that will be equal to theta B. If you try to draw again this elastic curve for this, it will be somewhat in this way over there, which will be having, if I draw tangential line to this, that will be showing the slope at point B that will be equal to theta B. Again, due to this theta B, what will happen? Rotations will occur at joint B and at joint A. That rotations will be how much? Now considering joint B and slope occurring at joint B, this end will be your near end moment and this end will be having your far end moment. So this will be equal to 4 EI theta B divided by L, and this will be equal to 2 EI, that is far end moment, theta B divided by L. Okay, now after this what I am doing, again I am maintaining the fixity at both the joints over there. I am maintaining the fixity at both the joints A and B. Only condition is what? During maintaining this fixity, I am releasing these two joints for my transverse displacements. What I am saying, that maintaining this fixity at joint A and B, but I am releasing my fixity for my transverse displacement at both the joints, that is at joint A and joint B over there. So due to transverse displacement, what rotations we have seen? Suppose if your point B is suffering over here, that is having transverse displacement B over there, due to that what will happen? This elastic curve will be bent in this way, and due to that what will happen? Your transverse displacement will be occurred at both these ends of intensity 6 EI delta upon L square. Same way 6 EI delta upon L square. The thing is what? Your this displacement amount at both the joint, that is at A and joint B, I am considering the same. So I am not writing here delta A or delta B, just simply I am noting it as delta over there, and depending on the direction of this acting, we need to give its sign over there. Okay, so either this will be plus or this will be minus, or either this will be plus or this will be minus. So I am writing plus or minus over here. Okay, now using the method of superposition over there, by superposition theorem we can say, by superposition theorem. Okay, what I have to do, I have to find out the final moment equation at joint A and final moment equation at joint B over there. Suppose final equation for joint A, that is my MAB, and final equation for my joint B, that is equal to MBA. Okay, so by using superposition theorem over there, what I can say, that is MAB will be equal to, just simply what you have to do, whatever moments I have got at this joint A, I have to cumulate these moments over there. Okay, so first MAB will be equal to what? First moment occurring, that will be equal to MFAB, right, plus second moment in that, that will be equal to 4 EI theta A divided by L, right. Third moment in that, that will be plus 2 EI theta B divided by L, and the last one plus or minus 6 EI delta upon L square. Okay, whereas MFAB, that is your fixed moment at joint A, 4 EI theta A upon L, that is your near end moment for slope A. This is your 2 EI theta B upon L, that is your far end moment for slope B, and plus or minus 6 EI delta upon L square, this is the transverse moment due to transverse displacement over there. So whatever this equation we are getting, that will be called as your basic equation of slope deflection method over there. Okay, same way we'll find out your second equation, that is for MBA over there, that is for joint B. Simply what you have to do, you have to accumulate again this all the values over there. So first value we will see MBA is equal to, first is your fixed moment at joint B, that is MFBA, plus next is your 2 EI theta A divided by L, plus 4 EI theta b divided by L, and next is your plus or minus 6 EI delta upon L square, which is occurring to your transverse displacement order. So that will be what? This will be your basic equation for your adjoint B, and this will be your basic slope deflection equation for your joint A over there. I'll try to modify this equation further also. See, can I write that is this will be equal to MFAB. Okay, in all these terms you need to multiply with flexural rigidity to zero. So instead of multiplying every time, what I'll do, I'll take common of that. So what I'll do, plus 2EI upon L, I'll take common from all these three terms over there. Okay, so what I'll get, 2EI upon L goes outside over there. So what here remains, that will remain 2 times of theta A, plus this 2A upon L, it goes outside, so that comes theta B, plus or minus what will remain here, that will remain 3 delta by L. Okay, so this you can treat as your modified equation of slope deflection for your joint A. Same way, if I try to modify this one, that is MBA will be equal to, same way, this first value as it is, that is MFBA, plus what I will do again, I will take 2EI upon L common from all these three terms over there. So what will remain here, first will be theta A, plus here it will remain 2 times of theta B, plus or minus it will remain 3 delta divided by L. So which will be your basic slope deflection equation for your joint B. You have to remember these equations over there. Further, for continuous beam also, that is first member is suppose your AB, next member will be suppose your BC over there. These equations will get modified at every type of joint over there. Okay, so depending on joint, what you have to see, just near end rotation 4ai theta upon L, far end rotation moment will be equal to 2ai theta upon L, and your moment due to transverse displacement, that comes equal to 6ai delta upon L square. So what you have to do, you have to use this method of releasing each member or each joint and maintain the fixity at each joint over there. This method is called as a method of relaxation. Okay, so these two equations you have to remember. So we'll end with your this lecture here. That was your basic equation for slope deflection method that we called as slope deflection equation. Okay, if you like this video, please like it, subscribe it, and if you have any queries, please comment it. Thank you so much.